Hey guys, this is going to be a video of me going over 1.1 through 1.4, the first homework assignment. Can't say I'm going to do this for every homework assignment, but hopefully you guys find this helpful. Or if you're stuck on a problem, you can use this video. Or if you need just more explanation. So, for number one, we have the size of a population of bacteria is modeled by the function p, where p of t, so the y-axis, p of t, gives the number of bacteria, and t, so the x-axis, gives the number of hours after midnight, t equals 0 to 10. So this is going to be midnight, this is going to be 10 hours after midnight. Okay, and the graph of the function p, so this is the function p, and a line tangent to p at t equals 8 are shown above. So here is our tangent line. A tangent line is a line that intersects a curve at exactly one point. Okay, and we're trying to find something that gives the best estimate for the instantaneous rate of change of p at t equals 8. Now, instantaneous rate of change is going to be, you can kind of think of it as slope at t equals 8 in this case. So we have this curve right here. What is the rate of change? What is the slope exactly at t equals 8? The slope of this tangent line is going to be the same of the slope of the curve at that point. So the slope of the tangent line is going to give us the instantaneous rate of change of the curve at t equals 8. And we learned that we're going to estimate slope of a we're going to estimate slope of a tangent line by using slope of a secant line. And a secant line is a line that intersects the curve at 2 points. So first of all, A does not work because P of A is going to give us the population of bacteria at t equals 8, and that's not giving me a rate of change at all, so that definitely doesn't work. The slope, go to B, slope of the line joining 0 and P of 8. So if we were to take the slope between those 2 points, now that's a secant line, and the slope of this line would be the average rate of change. Again, the slope of this line is the instantaneous rate of change. What's going to best estimate the instantaneous rate of change? This one, I guess you can argue, is an estimate, but it's not a good estimate. We're looking for the best. C, the slope of the line joining 0, p of 0, and 10, p of 10. So the slope of this line, which is the average rate of change for the first 10 seconds, that might be better, but it's not going to be our best. And then here we have the slope of the line 7.9. Now 7.9 is somewhere to the left of 8, and then 8.1 is zero point 0.1 to the right of 8. And if I had 2 points really close on the curve like that, if I were to do a tangent line right there, you can see that a secant line, sorry, the slope of that secant line will be very close to the slope of this tangent line. So this would be our best estimate right there. Question 2. A particle is moving on the x-axis, and the position of the particle at time t is given by x of t. So x of t is your position. So we have the position. It doesn't really specify units. Could be 10 feet, whatever it is. We could say 10 feet, 20 feet, 30 feet, 40 feet, 50 feet, 60 feet, or again, not really sure. We can just say units. And then time t is going, this is going to be in time. Again, not clear what the units are, but here's how I think about it. If you had like a straight line, just one linear dimension, and numbered from 0 to 60 right here, the position of the particle starts at 10. You can see that here. And in the first 6 units of time, the particle moves to position 40. So this particle right here just moves right to 40, and that's going to be within 6 units of time. And then you can see here that the position of the particle does not change from 40, from 6 to 10. So here, if the particle is not moving, you can say that the speed of the particle is 0. And look at the slope of this line. It's also 0. Now, whenever you see slope, whenever you have something that's like position versus time, the slope of the curve at any point is going to tell you the rate of change. So in this case, speed. And we're looking for the best estimate for the speed of the particle at t equals 4. So what is going to be the speed of the particle here? Well, we don't really need to estimate because this is already just a linear line and the slope is constant from 0 to 6. So I can find the slope of this line right here, and I'll find the speed of the particle at time t equals 4. So if I take the entire length of this line right here, which would be from 0 to 6, that's going to be the change in time. And then here is the change in position, which would be from 10 to 40, which would be 30 over 6. So there you go. You got your change in time over change in position over change in time, 30 divided by 6, and we'll get 5. So 5 is going to be the best estimate. It's actually not even an estimate. It is what the speed of the particle. It's the speed of the particle at that time. So 5. Question 3. A car is driven on a straight road, and the distance traveled by the car after t equals 0 is given by the quadratic function s, where s of t is measured in feet and t is measured in seconds from 0 to 12. Of the following, which gives the best estimate for the velocity of the car in feet per second at time t equals 6. So this is really not too different of a question than question 2. So here we had a particle that just moved on a straight line in a linear dimension. It just moved. It could move left or it can move right. Didn't necessarily have to just move to the right, but it did. In fact, you can see here that it moved to the right, and then it stayed, and then it moved to the right a little bit more. This is really no different. Imagine that you have this axis right here, and this one says that it's quadratic. So it's quadratic starting at t equals 0 all the way to t equals 12. So right here, this is a car moving on a straight road, or again, like a particle moving on an x-axis, so in a single dimension. It's really just the same thing. Okay, so what would be the best estimate? And here we have a couple of things. S of 6 would give us the position in feet at t equals 6 seconds, so not that one. B would give us the position at 6 divided by 6, not that one. And so these ones look to be rates of change because these are just formulas for slopes, or slopes of secant lines, right? So if you had this quadratic function, a quadratic function like this right here, t equals 6 right here. Here we have values from 8 to 4, so 8 to 4, and then we'd be finding the slope between those 2 points. But D would be even better because we have 7 to 5, which are closer to 6 in both directions. So the secant line here, the slope of the secant line right here would be the best estimate that we have for the velocity of the car. And velocity, again, it's feet per second. It's similar to speed. There is a difference though between velocity and speed, and we'll definitely get to that later. Alright, question 4. The graph of the function f is shown above. What is the limit as x approaches 2 of f of x? And we learned that a limit is not necessarily what's happening at, but what's happening near. And we have here x is approaching 2, so think about the function. What is the function doing? What is the values of the function? So you can see the values of the function as x is approaching 2. What are the values of the function approaching? And it appears that it is approaching 4. Remember that a limit is not concerned with what's happening at, but what's happening near the function. So what's happening near the value of x equals 2, not what's happening at. Okay, I have the following tables. So we have tables on the next page. Sorry, I know it's annoying. Which best reflects the values of a function g where the limit as x approaches 7 of g of x is equal to 6. So which of these best reflects that? Remember, we talked about tables, and tables never give a completed picture, so not always safe to assume. In this case, it's letting us know that we can. So we need to focus on these tables where x is approaching 7. So I'm gonna rule out option 8. So we have on the x-axis we have 5.85, and it looks like we're increasing, and then we get to 6, and then we don't get anywhere near 7. So this table tells us nothing about what's happening near 7. I think every other graph you can see here that we do have 7 within this domain. 7 is somewhere in between these two values right here. Okay, now we want to see the y values approach 6 from both sides. So if 7's here, we got to be approaching 6. We got to be approaching 6. Got to be approaching 6 from both sides. So D is out. This is approaching, I don't really know, maybe 15. Can't really tell for sure. From this side, it seems like these values are getting closer to 6. Okay, let's look at C. So these values right here, what do these values seem to get closer and closer to? That seems to be close to 6, but this seems to be 7. And then B, this seems to be getting close to 6, and this also seems to be getting close to 6. So B will best support this expression right here. Okay, moving on to question 6. Let f be a function that is defined for all real numbers x. Of the following, which is the best interpretation of the statement that the limit as x approaches 3 of f of x is equal to 5? Okay, so this is just basically making sure you know the notation here. So the values of the function f at x equals 3 is 5. That's not true. If I were to write that using appropriate notation, so that would be f of 3 is equal to 5. Nope. The value of the function, f of 5 is equal to 3. Nope, that's what's happening at. The limit wants to know what's happening near. So the limit so as x approaches 3, the values of f of x are approaching 5. I think that's going to be the one right there. We can see here x is approaching 3. X is approaching 3. The value of the functions are approaching 5. Okay. 7. The graph of the function f is shown above. Which of the following statements is true? So the limit as x approaches 1 of f of x is equal to 2.5. So right here, this seems to be testing our knowledge on one-sided limits, because we know that that a limit only exists if it's the same from the left and from the right. You can see from this graph right here that the limit as x approaches 1 from the left is equal to 2, but the limit as x approaches 1 from the right is 3. So the limit as x approaches 1 does not exist. Those are values are wrong. So let's see what C and D have to say. The limit as x approaches 1 of f of x does not exist because the left and right hand limits of f of x as x approaches 1 do not exist. I don't think that's quite right, because the left and right hand limits do exist. And D, the limit as x approaches 1 of f of x does not exist, because while the left and right hand limits of f of x as x approaches 1 exists, their values are not equal. There we go. That would be a good statement that sums up what's happening in this graph right here. Alright, question 8. The graph of the function f is shown above. What is the limit as x approaches 2 from the right? So this is the limit as x approaches 2 from the right. So what are the values of the function approaching from the right side? Seems like they are approaching 1. From the left side, it seems like they're approaching 4. And what's happening at seems to be 3. Question number 9. The graph of the function h is shown above. What is the limit as x approaches 4 of h of x? So let's look at from the left side. What's it approaching? 2. From the right side, negative 1. And so we're going to say it's non-existent. They're not approaching the same values. 10. The table above gives values of the function f at selected values of x. Which of the following conclusions is supported by the data in the table? So supported is a very important word there. Basically just means it's open to assumptions. Also, if you look at the available multiple choice answers, there's nothing that says that there's not enough data. Okay, so we're good to assume. So let's just look at these options right here. So we have the limit as x is approaching 4 of f of x is equal to 6. Well, let's take a look. So you can see that 4 would be somewhere in between these values, so we're approaching 4 from the left and from the right there. From the left side, it seems like we're getting close to 6. From the right side, it seems like we're approaching 7. So we can see that the limit does not exist, so I'm probably going to rule these out and jump straight to C or D, since it looks like these are one-sided limits and they're different. So the limit as x approaches 4 from the left appears to be 6, and the limit as x approaches 4 from the right appears to be getting closer to 7. So C, the data in the table is supported by C. The table above gives values of the function f at select values of x. Which of the following conclusions is supported by the data in the table? Let's see, the limit as x approaches 6, so 6 is somewhere in between here, so let's see how we're doing right here. These values right here, so from the left side, they seem to keep getting larger and larger and larger as we get closer to 6. And then from the right side, they seem to get getting smaller and smaller and smaller. So it seems like it's unbounded. One's going to get larger and larger to approach positive infinity. One seems like it's approaching negative infinity. So I'm going to say that it's likely that this does not exist. It's unbounded. Okay, let's try 12. The table above gives the values of the function f at select values of x. Which of the following conclusions is supported by the data in the table? So the limit as x approaches 11 and limit as x approaches 32 seems to be our option. X goes from 10 and it seems like we're approaching 10 to 12, so these are automatically out of the question, right? Because we're not approaching 32, but it does seem like the y values are approaching 32. But so the limit as x approaches 11, okay, it does look like those values are approaching 32. So I'm gonna say A. Okay, well, hopefully if you got stuck on any of those, you found this video helpful.